All right, so in chapter 7, we're looking at the normal probability distribution. So we have already looked at this kind of stuff all throughout the semester, okay? Because a normal curve is a bell-shaped curve, okay? So we've been looking at normal curves all semester, okay? So a lot of this will seem familiar. Some of the things that seemed really hard at the beginning of the semester are going to be so much easier because we've been repeating that information over and over and using it all semester. Okay? All right, so the first thing we're going to look at, though, before we get to a normal curve is a uniform distribution. Okay, so in this case, it says, suppose that the United Parcel Service, UPS, is supposed to deliver a package to your front door, and the arrival time is somewhere between 10 a.m. and 11 a.m. Okay? So let the random variable x represent the time from 10 a.m. when the delivery is supposed to take place. The delivery could be at 10. That would be x equals 0. Or at 11, that would be x equals 60. Okay, so there are 60 minutes in that hour from 10 a.m. to 11 a.m. Okay, with 1 minute intervals of time between x equals 0 and x equals 60 are equally likely. Okay, so if they're equally likely, that means there are 60 of these minutes in here, right? So if there are 60 of them, what's the probability that it will be delivered between, say, 10:01 and 10:02? That's 1 minute out of how many? 60. So the probability is the probability that x equals 10:01 sometime in that minute is 1 out of 60. Okay? So the probability that it's delivered at 10:02 is 1 out of 60. The probability it's delivered at 10:03 is 1 out of 60. Right, right. We're just considering minute intervals because that's what it told us to do. Okay? So because it says with all 1 minute intervals of time between x equals 0 and x equals 60 equally likely. That's why we're only considering minutes and not seconds. Okay? All right, so that is to say your package is just as likely to arrive between 10:15 and 10:16 as it is to arrive between 10:40 and 10:41. The random variable x can be any value in the interval from x equals 0 to 60. Okay, so any value from x equals 0 to 60. Because any two intervals of equal length between 0 and 60 inclusive are equally likely, the random variable x is said to follow a uniform probability distribution. Okay, so uniform means that all the probabilities are the same, 1 out of 60. Okay, so a uniform graph, a uniform distribution graph, you put the values 10 o'clock, 10:01, 10:02, 10:03 all along the bottom. And then the probability here is 1 out of 60, and it's the same for each bar. So when you do that bar graph, they are all 1/60th tall. Make sense? All right, so remember the total area under the graph. Each bar represents the probability from 0 to 1. So the probability of being delivered from 10 to 10:01 is the area of that bar. Okay, so if we have possible outcomes of 0 through 60, if we add up all their probabilities, what should they add up to? 1. So that means the area under this whole thing is 1. Okay? So, for example, if I want to know the probability of a package being delivered between 10:15 and 10:20, okay, that's a 5-minute interval. Okay, so that's 5 out of the 60 minutes. So the probability of it being delivered from 10:15 to 10:20 is 5 divided by 60, which is 1/12, or 0.0833. Make sense? All right. So let's say I want to find the probability of that it's delivered between 10:15 and 10:30. So how many minutes are between 10:15 and 10:30? 15. So 15 out of how many total? 60. So 0.25. So the probability that it'll be delivered between 10:15 and 10:30 is 0.25. Does that make sense? Okay, so that's a uniform distribution. This is a normal curve, a bell-shaped curve. So back in the second chapter, we started making histograms, bar charts where they touch, right? So in chapter 7, we're talking about continuous variables. Chapter 6, we were talking about discrete variables, okay? So that means that these variables can have all possible values in between, okay? And that's why these bars are touching, because it's a histogram. Bar charts, they don't touch. Histograms, they do, okay? Bar charts are for discrete data. Histograms are for continuous data. Okay? All right, so if you make a histogram and it ends up being bell-shaped like that, then we say that's a normal curve. All right, so remember the empirical rule that we talked about way back when? That's coming back, so don't forget it. But remember that one thing about the empirical rule is it was only true for bell-shaped curves, right? So this is a bell-shaped curve. A normal curve is a bell-shaped curve. So that means that 68% of my data is between within one standard deviation. So the mean is always in the middle of a bell-shaped curve or a normal curve. Mean is always in the middle. And then remember I said where it changes from being cupped down like that to being cupped up like it is on the sides? Where it changes is called the inflection point. And that's where one standard deviation more than the mean is. So the mean plus one standard deviation is here. The mean minus one standard deviation is here. Make sense? Okay, so that area in the middle there is 68%. What's the area under the whole curve? 100%, or 1. Okay, so because again, if you add up the probabilities of all possible outcomes, what does it equal? 1. Okay, so that's why the area under the whole curve is 1. But the empirical rule tells us within one standard deviation is 68%. How much within two standard deviations? Do you remember?
15?
More, because it's including more of it.
Oh, no,
Yeah?
90.
95 within two standard deviations. And then when you go out 3 standard deviations, 99.7. Almost all of your data is within 3 standard deviations. Okay? So here's the empirical rule on so you can see all 34 and 34, 68% within one standard deviation. Within 2 standard deviations, 95%. Within 3 standard deviations, 99.7%. Okay? Any questions on that? Okay, so here are some properties of the normal distribution. It's symmetric about the mean. So that means the mean is in the middle and it's the same on both sides. That's what symmetric means. It's the same on both sides. Okay? Because it's symmetric, the mean, the median, and the mode are all equal to each other. And we talked about that earlier in the semester too. When it's a bell-shaped curve, those three are all equal. Has a single peak, and that's at where x is equal to the mean. The inflection points where it changes from being cupped down to being cupped up on the sides, that where it changes is the mean plus 1 standard deviation and the mean minus 1 standard deviation. The area under the whole curve is 1. The area to the right of the mean is half of that because it's symmetric. So it equals half or 50% or 0.5. The area to the left, same thing, half, 50%, 0.5. Okay. As x increases or gets larger and larger, the graph gets closer and closer to the horizontal axis, but it never touches it. And same thing, as x gets smaller, it gets closer and closer, but never touches it. And then the last thing is that the empirical rule is true. Okay? So those are all properties of the normal distribution. Okay, so let's look at this data. I think we've seen this data before. The data on the next slide represents the heights in inches of a random sample of 52-year-old males. Draw a histogram of the data using the lower class limit of the first class equals to 31.5 and a class width of 1. And then the part B, do you think the variable height of a 2-year-old male is normally distributed? Okay, so these are all of the possible heights. All right, so it says to draw a histogram. So in order, and again, we did this back in chapter 2, but in order to draw a histogram of this, it says to use a lower class limit for the first class of 31.5. So if we make our classes, the first one's going to start at 31.5. And then it says to use a class width of 1. So then the next one, if you add 1 to that, 32.5, and then 33.5, and 34.5. So we're just adding 1 every time. 35.5, 36.5. Okay. There's a 38.9, a 39.3, so we need to keep going. 37.5, 38.5. Is there anything bigger than 39.3? No, I think that's, well, there's a 39.8. Yep, so we do need to go one more. 39.5. Okay. So then, because this is continuous data, remember we want the bars to touch. Okay, so where this one starts is where this one is going to end, because they're going to touch. Okay, so think of it as like if you have a big piece of cheese, you take a knife and cut it there. There's nothing at the cut, right? Everything's on one side or the other of it. So these are kind of like the cuts. Okay. So 33.5, 34.5, 35.5, 36.5, 37.5, 38.5, 39.5, and 40.5. Okay, so those are the classes. Then you would go through and you would count up how many of each of these points are in each class. Okay, so how many are between 30, we're not going to do all of them, but let's just do a couple of them. So how many of them are in between 31.5 and 32.5? And let me make this distinction too. 31.5 less than or equal to x less than 32.5. So it includes the lower limit, but not the upper limit. So there's just one in that. Okay. How many are between 32.5 and 33.5? There's one. There's another one. That one. So that's 3 so far, right? 4? Where, this one? No, not that one.
It's on the
Right side. This?
Yeah.
Okay, so there's 4. Okay, so you would go through and you would count how many in each one of those. And I would, if this was my homework, I would print it off so that I could cross off each one as I count it, and that way you make sure everyone is counted in here, and if you miss one, it's easy to tell which group it goes in. Yeah.
Wouldn't it be 31.5 to 32.4?
So,
Or is it because it's a histogram they're touching?
so it's because it's the kind where it's touching, because it's continuous, okay? So if I put 32.4, then where does 32.499 go? Nowhere. So see, I have to be able to include everything that gets as close as possible up to 32.5, but not including 32.5.
So would you
So
count for the second list too? That one.
So if there's
33.5 should go on the next one, not
right,
that.
33.5 should go here, not here. So did we count
So
it
that
here?
should be 3, yeah.
Okay, yeah. Okay, so let's just so 32.5 to 33.5 is going to include this one. 33.2,
33.0.
and this one. Okay, so it's going to include those 3. So that 33.5 is going to go in this one. Okay? Good catch. All right, any questions about counting the frequencies? Okay, so in order to draw the histogram, I would have to count each one, and then along the x-axis, I would put these classes, and so on this one, this is actually a relative frequency histogram because it has the percents over here. So remember, how do we find relative frequency?
Dividing in frequency by how many we have.
Right, so how many are here? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. So that's 48, 6 times 8, plus 2 more, so 50. So the relative frequency is going to be 1 over 50, and 3 over 50, and so on. So what's 1 over 50? 0.02. So what percent is that? 2%. Okay, so if you look, this bar between 31.5 and 32.5 is 2% tall. Make sense? So that's how you would build a histogram. Of course, you can do that in StatCrunch and also on your calculator. The drawback of using your calculator to make a histogram is that you can't determine the width of your classes. On StatCrunch you can, but on this you cannot. Okay. All right. So the second question then, after you make this histogram, is that normal shaped? Is it bell shaped? Yes. Okay, so if I were to draw a bell shape over that, it would be bell shape, which is what they did on this slide. Okay. So is it perfectly bell shaped? No, but the way we say that is that it's approximately bell shaped. If you can draw a curve over that, like this one is a little bit shorter than that one, so it's not perfectly bell shaped, but it is approximately bell shaped. Okay. All right, so when we think about the height of these, when I did the height of it, I found the relative frequency, which is, that's called the proportion. So the height of that bar is the proportion of values that are in between 31.5 and 32.5. Okay? It's also the percentage. And there's one more P that represents. What does that decimal represent? The probability. Okay? So 3 P's, probability, percentage, and proportion. So when I find the relative frequency, I'm finding the probability, 0.02. The proportion is 1 out of 50. Okay, or 0.2, depending on how you write it, but those both mean proportion. And then when I move the decimal 2 places, that gives me the percentage. So that relative frequency tells me those 3 things. So when it asks you what to interpret the area under the curve, those are the 3 interpretations. Okay, PPP, percentage, probability, and proportion. All right. So let's look at this example. The weights of giraffes are approximately normally distributed with a mean of 2,200 pounds and a standard deviation of 200 pounds. Draw a normal curve with the parameters labeled. Then shade the area under the normal curve to the left of 2,100 pounds. And then suppose that the area under the normal curve to the left of 2,100 pounds is 0.3085. Provide, I'm going to say not 2, but 3 interpretations of this result. Okay? All right. So I did part 1 over here. Get used to drawing normal curves. Draw every time that you read a problem and it says anything about being normally distributed, draw a normal curve and put a line down the middle of it to represent the mean. Okay? All right. So just because it might help seeing me draw that, let's go ahead and draw that. So a straight line goes up in the middle and down like a bell. And then it's supposed to not ever touch. It just gets closer and closer. Right down the middle is the mean. And in this case, that's 2,200 pounds. The standard deviation is 200 pounds. And remember, standard deviation, the one standard deviation is where it changes from being cupped down to then being cupped up. Okay. So if I take 200 and add it to 2,200, what is this going to be here? 2,200 plus 200? 2,400. Okay. If I take 200 and subtract it from the mean, what do I get over here? 2,000. So those are x values. Okay. So how much of my data is in between there? 68% of the giraffes weigh between 2,000 and 2,400 pounds. Make sense? Okay. So then the second part of this said to shade the area under the normal curve to the left of 2,100 pounds. So where does 2,100 fall?
In the middle of 2000 and
So right in the middle here is x equals 2100. Okay? So then the area to the left of that is what we want to shade. Okay? So then it says, suppose that the area under the normal curve to the left there is 0.3085. Does that make sense? Because the mean is right there in the middle, and remember the area to the left of the mean is 0.5. So this part to the left of the mean has to be less than 0.5, right? So it makes sense for it to be 0.3085. Okay, so what are the three interpretations of that area then? The three P's. Proportion, percentage, and probability. Okay, so the proportion of giraffes that weigh less than 2,100 pounds is 0.3085. Okay, the percentage of giraffes that weigh less than 2,100 pounds is 30.85%. Okay, the probability that a giraffe weighs less than 2,100 pounds is 0.3085. Make sense? So depending on what question they ask you, you're going to give one of those three answers about that proportion there, that shaded area. Okay? So in this chapter, that's what it's going to be all about, is finding shaded areas, okay, and finding the cut points, okay. So in section 7.1, we're going to talk about the finding the area, okay. So if I give you that cut point and the mean and the standard deviation, then you can find that area, okay. And we have a couple different ways to find that. Okay, so first we're gonna we're gonna look at finding and interpreting the area under a normal curve. Okay, and then finding the value of the cut point, which is the normal random variable. Okay. All right, so since way early in the semester, we've been finding z-scores, right? So a z-score fits on a normal curve. So remember, if you have a z-score to the right of the mean, what is that? Is it positive or negative z? Positive. And if you have a z-score to the left of the mean? Negative z. And what does the z tell me? The number of standard deviations to the right if it's positive, or the number of standard deviations to the left if it's negative. Okay? All right. So be sure and write this down. Really, you should memorize that. And you probably have done it enough that you already have it memorized, but it's right up here at the top right corner of your formula sheet, because it's probably one of the most important formulas in statistics, if not the most important. Okay? All right. So we talked about z values are positive to the right and negative to the left, and they represent number of standard deviations. Okay, so once you, another important thing is when you're talking about z values, the mean is always 0 and the standard deviation is always 1. Okay, if you're putting z values on your normal curve, then the mean is always 0 and the standard deviation is always 1. All right, so here's an example. IQ scores can be modeled by a normal distribution with mean equals 100 and standard deviation equals 15. An individual whose IQ score is 120 is 1.33 standard deviations above the mean. Okay, so I drew, as soon as I saw those words normal distribution, first thing I do is draw a normal curve. Then put in the middle, the mean is 100. Then the standard deviation is 15, so that means if I add 15, I get 115. If I subtract 15 from 100, I get 85. Okay, so that's the first thing I do when I read a word problem and I see normal distribution, is I start drawing that bell-shaped normal curve. Okay, then it tells me that an individual whose IQ score is 120, so 120 is out here to the right of the mean. 100 is here, 120 is more than the mean, right? So it's over here. So that, since it's more to the mean, more than the mean, then the z-score is going to be positive because it's to the right of the mean. But to find that z-score, you use the formula 120 minus the mean is 100 divided by the standard deviation is 15. So 120 minus 100 is 20 divided by 15 is 1.33. So that's how you change an x value of 120 into a z-score of 1.33. Okay, so every x value, you find the corresponding z-score, or how far it is, how many standard deviations it is away from the mean, by using this formula. Okay, any questions on that? All right. You can also use your table, so go ahead and get your formulas out, and the second and third pages are z tables. Okay, so when you use these z tables, if I look up z equals 1.33, that was here, z equals 1.33, so you go down along the left side of the z table to find 1.3 for the ones digit and the tenths digit, and then you go across the top to find the hundredths digit, 0.03. Okay, so one point where that column, the 0.03 column and the 1.3 row meet is 0.9082. So what that tells me is that the area, if you look up at the top of this table, it shows you what the table's giving you is the area to the left of that z-score. Okay, so the area to the left of that 1.33 is 0.9082. So if you have a normal curve, the mean was 100. The mean IQ score is 100. The standard deviation is 15. And then we said one individual has an IQ score of 120. Okay, so 120 is out here somewhere. X equals 120. I changed that to a z. by taking the x value minus the mean divided by the standard deviation to get 1.33. Then you look at the table. So if I want to know the probability that x is less than 120, then I would change that 120 to a z, so probability that z is less than 1.33. Those are equal. This probability and that probability are equal. The probability that x is less than 120 is the same as the probability that z is less than 1.33. The reason that we change it to a z-score is so that we can use this table. Okay? So then you look up 1.33 and you find that the area to the left, this shaded area here, 1.33 is 0.9082. So that means the probability that z is less than 1.33 is 0.9082. Okay? Which is the same as the probability that x is less than 120. Any questions on that using the table? Okay, so let's say this is the probability that a person has less than 120 IQ score. Let's see what is the probability that a person's IQ score is greater than 120. Okay, so remember that 120 has a corresponding z-score of 1.33. Okay, so I change it, the x to a z and the 120 to 1.33. Using the way I got that, again, is using that formula for z. X minus mean divided by standard deviation. Okay, so what's the area under the whole curve? 100% or 1, right? So if I want to know this area, I'll shade it differently. If I want to know that area, how do I find that if all I know from the table is the area to the left? Subtract it from 1. 1 minus 0.9082. So what does that equal? 0.91. What? Say it again. Oh, okay. 0.0918. Okay.
And how did you say you got the 0.90982?
I looked up the z-score of 1.33 on the table. So 1.3 and then go to the hundredths places along the top. 1.3 and then the 03 where that column and this row meet is 0.9082. Does everyone see that on your table? So z equals 1.3 is along the left column, and then the hundredths digit is the 0.03 along the top. That's the right column. Make sense? Okay, so the table always gives you the area to the left. So if you want the area to the right, you have to subtract that area from 1. Any questions on that? Okay, so you can use your calculator to find those areas too. You don't just have to use the table, and there are limitations to the table, because if I have 1.331, my z value, well, I just have to pick what's closest to it. I can't, there isn't it only goes to the nearest hundredths place on the table, okay? All right, so if I want to know the probability that x is less than 120, okay, I'm going to go ahead and just draw the curve again just so nobody's confused. well, that's not a very good one, but use your imagination. The mean in the middle is 100. Standard deviation is 15. Okay, I want x is 120. I want to know the probability that x is less than 120. Okay, so okay, so the probability that x is less than 120. Okay, so again, changing that to a z-score, x is less than, or z is less than 1.33. Okay, so, and that I found using the formula z equals x minus mean divided by the standard deviation. Okay, all right, so if I use my calculator to find this, using that x value that has a corresponding value of z equals 1.33. Okay, so using the x value, you go to second distribution, and then you put in the area at the lower boundary of the shaded area, then the upper boundary of the shaded area, then the mean, and then the standard deviation. Okay, so this shaded area keeps going out. Remember that it doesn't ever touch the x-axis. It gets closer and closer and closer, but it never touches it. Okay, so the lower boundary is actually negative infinity. It keeps going out. But I can't put negative infinity into my calculator. I forgot. Second distribution, normal CDF, cumulative density function. It's a whole area accumulated. Okay. All right. So second distribution, normal CDF, and then you put in the lower boundary. Well, since we can't put in negative infinity, what we put in instead is negative down here at the bottom, and then 1, so negative 1, and then second, this double E is the comma key, and then 99. So negative 1 E99. That represents negative infinity. It's negative 1 with the decimal moved 99 places to the right. That's what that means. Okay, so it's a huge number, but negative. So a huge small number. So negative 1 E99 represents negative infinity for the lower boundary. Okay, the upper boundary, because we're using the x's right now, we're not using the z's. The upper boundary is this x equals 120. Okay, and then because that is an x value, and I didn't change it to z yet, I use the mean that was given to me of 100, and the standard deviation that was given to me of 15. Okay, so when you do that, what do you get? Okay, so second distribution is below your arrows key. Normal CDF is the second one. Negative 1 E99 is the lower boundary. The upper boundary, 120. The mean is 100. And the standard deviation is 15. Okay, good. So that equals 0.9088. Thank you. Okay? So that means that this area is 0.9088. Okay? It's a little bit different than what I got from the table, looking up 1.33. And again, that's because of the rounding errors on the table. Okay, so so if you're using your calculator instead of the table and it's a multiple choice question and the closest thing that it has is 0.9082, then choose that one. Okay, and show all your work so that I can know. Okay, any questions on that? So what does this mean, 0.9088? Three interpretations of it. So the proportion of people that have an IQ score less than 120 is 0.9088. The probability of having an IQ score of less than 120 is 0.9088. The percentage of people that have an IQ score of less than 120 is 90.88%. Okay, make sense? All right. So if I want to do the same thing in my calculator using the corresponding z-score, you would do second distribution, and then the lower boundary is still going to be negative infinity, so -1 E99. And then the upper boundary, instead of using the x value, we're going to use the z-score, 1.33. So since I put in a z-score, what does the mean have to be? When we're talking about z-scores, the mean is always 0, and the standard deviation is always 1. Okay? So what do you get when you put that in? 0.9082. So why did we get 0.9082? The same thing that we got from the table here, but not here. But not here. Because we put in a rounded z value, right? So that z-score is a rounded number. So we put in the same value that we use on the table, which is 1.33. Okay? Here, we're not putting in a rounded value, it's calculating it for us, and so it's carrying everything out to more decimal places. So I would accept either answer like that. StatCrunch will accept either answer like that. But on a test, be sure and show your work of how you did it. Yes?
So we go second distribution, and what do we do after that?
You put in the lower boundary of your shaded area.
But are you in normal CDF?
Number 2.
on the-
Oh, normal CDF, yes.
Yeah.
Normal CDF for both, sorry.
Okay.
Normal CDF. Yeah, it's the same whether you're using the z-score or the x value. The only thing that changes is the mean and the standard deviation. So if you're using the z-score, the mean is always 0, the standard deviation is always 1. If you're not using the z-score, then you put in the mean and standard deviation that were given to you. Okay? All right, any questions on that? Okay, so we did that. Go ahead and move on. Okay, we already did that. Okay, let's look at this one. So the area under the standard normal curve, so when it says standard normal curve, that means z values. Okay, standard is, since you're standardizing everything, changing it to z-scores, then no matter what your mean and standard deviation was, when you change it to z-scores, it standardizes it so that we can use the z-table. Okay, so that's why it's called a standard normal curve. All right, So find the area under the standard normal curve between z equals negative 1.2 and z equals 2.94. Okay, so it says it's a standard normal curve. So I'm going to start off by drawing a normal curve. Then put in the z values. So it says z, well, first put in the mean always. Then the z is negative 1.02 is going to be to the left, about 1 standard deviation. So z equals negative 1.02. Then z equals 2.94, that's almost 3 standard deviations. So 1, 2, 3, almost 3. So z equals 2.94. So you just estimate this. This is just to help you visualize it, okay? And then we're trying to find the area under the curve between those two. So that's what we're looking for. So if you put that in your calculator, second distribution, what's the lower boundary?
Negative 1.02. No.
Yep. What's the upper boundary?
2.94.
Okay. What's the mean?
0 and 1.
0 and 1, because these are z-scores that I put in there. So 0 is the mean, 1 is the standard deviation. And I keep forgetting for some reason to write normal CDF.
Yes.
Sorry. Okay, so second distribution, normal CDF, the lower boundary of our shaded area, the upper boundary of our shaded area, and then 0 and 1.
0.8445.
Okay, 0.8445?
Yeah.
Okay. All right. So that's how you would find that using the calculator. If you want to use the table, you would look up z equals 2.94. Okay, and that's going to give you the area all the way to the left from that. Okay, so it's including all of this, all the way down there. Okay, so 2.94. Look it up on your table. 2.9, and then go over to the column of 0.04. So what do you get there? 0.9984. Okay, so 2.9, and then I went from let me find the top up here, 0.04, go down that column until that meets up with the 2.94. Okay, so 9984. Okay, so that gives me 0.9984 is the area all the way over to here. Okay, then if I look up z is negative 1.02, it's going to give me this area to the left. So then you go to your negative z table. We're looking at negative 1.0 and then over to the 2 column. So negative 1.00, negative 1.01, negative 1.02. So 0.1539. Okay, so to the left is 0.1539. So using the table, then the area in between here is going to be 0.9984 minus this little piece over here, 0.1539. So when you subtract those, what do you get?
0.8445.
Okay, whoop. So same thing that we got using the calculator. And that's because the z values that we put in are rounded to the nearest hundredths place already. Okay, so that's exactly the information that the table has. Any questions on finding the area in between? Okay, so we found the area to the left. We found the area between two scores. How would we find this area to the right? How did we find it before?
Subtracting whatever is there.
Uh-huh.
1 minus that.
So we can do it that way. We can subtract it from whatever the area is to the left, or using your calculator, you can also use the lower boundary and upper boundary, but instead of negative 1e99 for negative infinity, you're going to use positive 1e99.
Would you do PDF or CDF?
CDF. Did I say PDF? I'm sorry. Okay, so let's go ahead and do that. I was trying to find an example, but we'll just use this one that we were using before. Okay. So let's just use the proportion of giraffes. Okay, so the giraffes that we talked about before, let's say that we want to find the probability that a giraffe weighs more than 2,100 pounds. Okay, so the mean is in the middle, 2,200 pounds. The standard deviation was 200 pounds. So 2,100 pounds is less than the mean, so it's over here. So x equals 2,100 pounds. Okay, so if I want to know the probability that the weight of the giraffe is greater than 2,100 pounds, then I would be looking at the area to the right over here. Okay, so I could use normal CDF, so second distribution, normal CDF, then what's the lower boundary of this shaded area? What's this boundary right here? 2,100. Okay, so that's the lower boundary. What's the upper boundary? It's positive infinity, right? Because this keeps going out. So can I put positive infinity in? No, so I put, instead of negative 1e99, you're going to go second distribution, normal CDF, lower boundary is 2,100, upper boundary, instead of negative 1e99, I'm just going to do 1, second, comma key for the e, 99. So that's 1, and then move the decimal 99 places to the right, right? So that's a huge number. And then the mean is 2,200 for the giraffes, and the standard deviation is 200. Then enter, and if you have a TI-83, you would put it in like that with commas in between it. Okay, so lower boundary, upper boundary, mean, and standard deviation. And then close your parentheses and enter. So 0.6915. Okay, so this area to the right here is 0.6915. All right. So that's the probability that a giraffe weighs more than 2,100 pounds. Any questions on that?
So what's the difference between non-PDF and CDF?
So PDF just tells you the probability that a giraffe weighs exactly 2,100 pounds. Okay. So usually in continuous distributions, we don't do a whole lot of equals. Most of it is less than or greater than or in between. Because like I was saying, the analogy with the cheese where you cut it, there's really no value there. It's just a cut point. So all of the data is above or below that. Okay, so another idea that we've talked about before is percentiles. Okay, so a percentile, so for example, if something is the 71st percentile, that means that that's the cut point. Okay, that's where the Z value there cuts off 71% of the data. So if your X value is this value here, then that means 71% of the data is less than that. So if it's P sub 71 is how you would write that. Okay. So the 71st percentile means 71% is less here. So in this case, we know the area to the left is 0.71. Okay, everything we've looked at up until this point, we knew the cut point, but we wanted to find the area. But if they give you the percentile, then you know the area, but you don't know the cut point. So that's what you're going to be looking for. So you're kind of going backwards. Okay. So this is the procedure for finding a value of normal random variable, which is the X. It's that X value there. Okay. So first thing you want to do is draw the normal curve. Shade the area corresponding to the proportion, probability, or percentile that they give you. Okay? So if they give us 71st percentile, I'm going to put the 71 here and shade it. So remember that the mean is always in the middle, and half of the data, or 0.5, is to the left. So if this whole thing is 71, half of it is over here, 0.5. That leaves 0.21 of it right here. Okay? All right. So first you draw the normal curve, shade the area corresponding to the proportion, probability, or percentile you're looking for. Then you use table 5 to find the z-score that corresponds to the shaded area. And then you obtain the normal value using this formula, which is on your formula sheet. Right, it's the second one underneath here. So really all they did is take that z-score formula and solve it for x. Okay, so they multiplied both sides by standard deviation to get the z times standard deviation, and then they added the mean to both sides. That's how they got this formula. Okay. All right, so let's look at an example. All right, so the combined verbal and quantitative reasoning score on the GRE is normally distributed with a mean of 1,049 and a standard deviation of 189. What is the score of a student whose percentile rank is the 85th percentile? Okay, so they give you, first of all, it says normally distributed. When it says normally distributed, the first thing you're going to do is draw yourself a normal curve. Put in it the mean that they give you. Put in the standard deviation that they give you. Okay, and then it says, what is the score of a student whose percentile rank is at the 85th percentile? So that means the area to the left of him or her, the student, is 85%. So where's that cut point going to be? To the right or to the left of the mean? To the right. Okay, because 50% is over here, right? So how much more do we have over here? Another 35%, right? Okay, so this area is 85% or 0.85. So what we want to know is what's the cut point there? What is that student's score in order for them to be in the 85th percentile? Okay? All right, so you can use the table to do this, but again, the table is limited. So is this z-score that corresponds to this, is that z-score going to be positive or negative? Positive. So you're going to go to the positive z table and you're going to look for an area of 0.85. Okay? So when you look at the positive z table, the column, first column and the top row represent the z value. But these numbers in the body of the table represent the area. So you have to look at through those numbers and try to find what's closest to 0.85. Okay, so let's see. Here's 0.8508. Here's 0.8485. So what's the closest thing to 0.85? Okay, so the corresponding z-score to that then is 1.0. And then up that column is 0.4. So 1.04 is the z-score that corresponds to that. Okay? But really, this is giving me the 85th percentile, not the 81st. Right? Yeah, this is 85th percentile, which is what we're looking for. So, again, this table is limited because this is 85.08. Which is pretty close, but sometimes you're not going to be able to get as close. Okay? All right, so 1.04 is the corresponding z-score from the table. Okay? All right, so if that's the corresponding z-score, then what is the corresponding x value or test score of that person? Okay, that's where you're going to use this formula. So x equals the standard deviation times z plus the mean. So then just fill in everything you know. You're looking for x. The standard deviation is 189. The z-score that we found from the table is 1.04. Plus the mean is 1,049. Okay, so 189 times 1.04 and then plus 1,049 is 1,245.56.
How do we get the z-score without the table?
Okay, so you can do that without the table. You can do that with your calculator. So the way that you find it with your calculator is you, if you know the area, but you're looking for the cut value, then you use inverse norm. Okay, so go to second distribution and go to inverse norm. Okay, so using calculator, second distribution, inverse norm, and then you're going to put in the area to the left and the mean and the standard deviation. Okay, so inverse norm, in this case, the area to the left is 0.85. The mean is 1,049, and the standard deviation is 189.
And we looking for the right, the left.
Okay, so if you do inverse norm, the area is to the left, right? So 0.85. The mean is 1,049. The standard deviation is 189. The tail is on the left, okay? So most calculators don't give you that option of left, center, and right, but these plus CE calculators do. So if you don't have that, don't worry, just always know that that area is the area to the left, okay? You have to enter the area to the left in the other calculators. Okay, so that gives me 1,244.89. Okay, so what that gave me is the cut score, because I entered the X value in there, the mean and standard deviation for the X value. Okay, if you wanted to specifically find the Z-score, then you would also use inverse norm, but for the mean and standard deviation, you would put 0 and 1, and that would give you something close to 1.04. Okay, so if you do second distribution, inverse norm, 0.85 for the percentile, and then mean 0 and standard deviation 1, and left and paste. So that gives me, so let me go ahead and put it over here, inverse norm, area to the left 0.85. This is to find Z. This is to find X. The difference is what you put in for the mean and the standard deviation, okay? So the mean, if I'm trying to find Z, is 0 and the standard deviation is 1. And that gives me 1.03643, okay? So that rounds to 1.04 that we got on the table, okay? So that gives me the Z-score that I can then plug into this formula, okay? But if you go ahead and put in the mean and standard deviation for the X values, then it's going to go ahead and give you the X value. So what does this mean? So if I round that 1,240, well, this one would round to 45, and this one would round to 46, and this one would round to 45, right? Okay, so that means that the cut score, the person who got a score of 1,245 or 1,246 is in the 85th percentile, okay? And again, it's because of the limitations of the table that this number is off, has a little bit of rounding error, okay? Any questions on that? Okay, I think that is pretty much everything that you need for section 7.1 and 7.2. The only thing that we didn't cover is 7.3, and we will cover that on Wednesday. There are only 2 problems on your homework for that, and I'll show you how to do that on StatCrunch, so it won't be too difficult.